Alrighty, everyone. So, hello and welcome to the first of the virtual lectures. So I'm going to be going through the PowerPoint for sections 4.1 and 4.2, minima, maxima, and the mean value theorem. If at any point you want to attempt a problem before I go over it, just pause the video and resume it when you are finished. So, in this next section, we're going to be dealing with some more applications of derivatives. Last section we did related rates, which is a major application of derivatives, but it is not the only one. So we've learned a bunch of this stuff before, that derivatives, specifically the first derivative, but the second derivative as well, can tell us a lot about the behavior of the actual function. So none of this is new information. This is all just a recap of things that you have learned previously. So if a function is increasing on a particular interval, that means all of the slopes of the tangent lines are positive, and that means the derivative is positive. So if the derivative is positive at a specific point or interval, that means the function is increasing. If the first derivative is negative at a point or interval, that means that the function is decreasing. And there are a bunch of different scenarios that could yield a derivative being equal to 0. And we've seen a couple of them so far. So for one of them, the graph could look something like this. Hold on, my stylus is malfunctioning here. There we go. So for one of them, the graph could look something like this. So at this minimum right there, the tangent line is equal to 0. So at this minimum, the derivative is equal to 0. Also, we have maximums. So at this maximum right here, the tangent line is horizontal, so the derivative is equal to 0. Now, those are not the only ones. We have what are called saddle points, which go something like this. Think y equals x cubed and its behavior right in the middle. Where it flattens out right in the middle, because it flattens out, that means it is horizontal, and that means that the tangent line is horizontal, and the derivative is equal to 0. And, it can go the other way as well, so think the graph of y equals negative x cubed, and you have that point right there. We're going to get a more formal name for these points later, but for now we're going to informally call them saddle points. And then also, remember that the derivative of a constant is equal to 0, so constant functions, or a function that has an interval where it flattens out and becomes constant, also has a derivative that equals 0. So there are a lot of scenarios that will give us a first derivative being 0. Now, we're going to be focusing first on what is called absolute extrema. Extrema is an umbrella term for absolute maximums and absolute minimums. And really, this is the technical definition for absolute maximums and absolute minimums, but in essence, on a closed interval, which is a piece of a graph, meaning it has an endpoint on one end and an endpoint on the other, the absolute maximum is the highest point on the graph. So the absolute maximum would have the biggest y-coordinate of all of the points on that particular closed interval. So, for example, here, this is the highest point on the graph. This point has the biggest y-coordinate, so that is the absolute maximum. The absolute minimum on a closed interval is the lowest point on the graph, and it is the point that has the lowest y-coordinate, or the smallest y-coordinate. So this point here on this closed interval, since this is the lowest point and has the smallest y-coordinate, this is the absolute minimum. So if you have, let's say, an open interval, your absolute extrema are not necessarily guaranteed, but some graphs have one, some graphs don't. So for example, y equals x squared on its domain negative infinity to infinity, it does have an absolute minimum. Y equals x squared has this vertex here at 0, 0. So what that means is 0, 0, there is no point on the graph of y equals x squared that is lower than that vertex. So since there is no y-coordinate that is smaller than this, this is the absolute minimum. This is the lowest point on the graph, so there is an absolute minimum of 0 at x equals 0. The value of the absolute extrema is the y-coordinate, and it occurs at the x-coordinate. So the absolute minimum is 0, and it occurs at x equals 0. Now, because this graph does increase forever and ever and ever without bound, that, on both sides the graph approaches infinity as x gets bigger and bigger. There is no absolute maximum. However, as soon as we look at what's called a closed interval, which is only a piece of the graph, we are suddenly guaranteed to have both an absolute minimum and an absolute maximum. So this little piece right here is the graph of y equals x squared on the closed interval 0 to 2. So this right here is the smallest y-coordinate, or the lowest point, so that is the absolute minimum. So there's an absolute minimum of 0 at x equals 0. This right here is the highest point on this interval, and it has the biggest y-coordinate, so there is an absolute maximum of 4 at x equals 2. Now, only on closed intervals are you guaranteed to have both. As soon as the interval becomes either half open or half closed, or completely open, you're not guaranteed to have both an absolute maximum and an absolute minimum. So for example, same y equals x squared on the open interval of 0 and the closed interval of 2. So it's open at 0 and closed at 2. We do have an absolute maximum. Because this endpoint is included, that means there is an absolute maximum of 4, and it occurs at x equals 2. However, because this point down here is not included, there is actually no absolute minimum. Because yes, you can get closer and closer to 0, and yeah, the limit exists. We're not really dealing with limits here, we're dealing with actual y-coordinates. Yes, it is getting closer and closer to 0, but since you can get infinitely closer and closer to 0, but never actually reach it because this point is not defined, there is no true absolute minimum. And then over here for y equals x squared on the completely open interval 0 to 2, in this case there is no absolute maximum and there is no absolute minimum, because again, if that point's not included, you can get closer and closer to it but never actually reach it. And that point is also not included. Absolute extrema do not have to occur at the endpoints of the interval. For this example over here, it did because just because of the shape of the graph, but that's not always going to happen. Absolute extrema can occur in one of two places. They can occur either at endpoints of the closed interval, or they can occur at interior points. So for this first graph right here, this is an example where the absolute maximum and the absolute minimum are interior points, meaning points that are between the two endpoints. So this point right up here, this is the highest point on the graph, the biggest y-coordinate. This right here is the absolute maximum. And it is an interior point. And this point down here, this has the smallest y-coordinate, it is the lowest point on the graph, and it is the absolute minimum. So they are interior points. Now for this one over here, we have this endpoint over here at A and this endpoint over here at B. This endpoint over here at A is the biggest y-coordinate, highest point, so this is the absolute maximum. And this one down here, this is the smallest y-coordinate, or the lowest point, so this is the absolute minimum. So this is an example where the absolute extrema occur at the endpoints. Now, it's not necessarily, doesn't have to be one or the other, you can have a mix of the two. So for this next one down here, this point right here, this endpoint is the lowest point on the graph, so that is the absolute minimum. And it is an endpoint. However, the absolute maximum is right here. This is the highest point on the graph. So in this case, the absolute maximum occurred at an interior point, and the absolute minimum occurred at an endpoint. And then this one, over here on the bottom right, is also a mix of the two. This is the absolute maximum right here. This is the highest point on the graph, and that is an endpoint. And the absolute minimum is down here at this interior point. Now, for all the examples that I showed you previously, they were all continuous functions on closed intervals. Now, as soon as you have a point of discontinuity, even if the interval is closed, you are not necessarily guaranteed to have both an absolute maximum and an absolute minimum. You might still have one or the other, you might not have either, or you might not have both. So for example, this first graph over here on the left, this is a closed interval, technically. It does have a point of discontinuity right here at 1. You've got, this jump going on. So there is an absolute minimum. the absolute minimum is actually 0. And yes, you can have more than one point be an absolute minimum or maximum. If you have 2 points whose y-coordinates are the same and they are both the smallest y-coordinate, they can tie for absolute minimum. So there are 2 points that are the absolute minimum. So the absolute minimum is 0, and it occurs at x equals 0 and x equals 1. Now, because this point up here is not technically included, it technically doesn't exist, there is no absolute maximum, because remember, you could get closer and closer to it and never actually reach it. So as soon as you have a point of discontinuity, there was an absolute minimum, but there was no absolute maximum. Now for this graph over here on the right, yes, this interval is technically closed from A to B. There is an absolute minimum down here at A. This is the smallest y-coordinate. However, because that point technically does not exist and is not included, there is no absolute maximum. So if you have a point of discontinuity, you are not guaranteed to have both an absolute minimum and an absolute maximum. And all of that can be kind of summarized in an extremely important theorem called the extreme value theorem. And here's what the extreme value theorem says. If a function is continuous on a closed interval a to b, then it is guaranteed to have both an absolute maximum and an absolute minimum. The key is there are 2 conditions in order for the extreme value theorem to even apply. The function needs to be continuous, so no points of discontinuity like you saw in the last example, and the interval needs to be closed. I'm sorry, my handwriting is not the best. It is very disorienting writing with a stylus. So if you have a function that is continuous on a closed interval, the function is guaranteed to have an absolute maximum and an absolute minimum on that interval. So for each of these, what we're going to do is we're going to state whether the extreme value theorem even applies, and regardless of whether or not it does, we're going to identify the absolute minimum and the absolute maximum, or explain why there aren't any. So for this first one on the left, y equals f of x, we're going to see if the extreme value theorem even applies. So first of all, if you take a look, if you trace the graph from left to right, I never have to lift up the pen, so it is continuous. And the interval is closed. This endpoint is included, and this endpoint is also included. So because the function is continuous and the interval is closed, the extreme value theorem, which I'm going to abbreviate as EVT, does apply. So because the extreme value theorem does apply, we are guaranteed both an absolute maximum and an absolute minimum. So the absolute maximum is going to occur here at A, because this is the biggest y-coordinate, the highest point on the graph. Now the absolute minimum is going to occur down here at C, because this is the lowest y-coordinate, and the lowest point on the graph and the smallest y-coordinate. Now for this function over here, y equals g of x here on the right, we have a point of discontinuity at C. We've got this jump discontinuity, so right away, because the function is not continuous, the extreme value theorem does not apply. And even worse, the interval is not even closed, because this endpoint at A is not included and this endpoint at B is not included. So extreme value theorem just does not apply. However, that doesn't necessarily mean that we won't have one of the other absolute extremas. We're just not guaranteed to have both. We do have an absolute maximum. It is right there at C, because this right here, this point is included, and it is the highest point on the graph. However, if this point were included, it would be the absolute minimum, but since it's not technically included, there is no absolute minimum. Now, absolute extrema are just the highest and lowest points, respectively, on a graph. They might be the same as what are called local extrema, or they may not be. So absolute extrema and local extrema do have some overlaps, but they are technically different. So I just want to get that out of the way right now. Local extrema are a little bit different. Local extrema occurs at what are called peaks and valleys. So local extrema looks something like this. Peaks like this, and valleys like this. A local maximum occurs at a point like this. A local maximum occurs when its y-coordinate is the biggest among all of the points that are immediately nearby. Not necessarily on the highest point on the entire graph, but at a local maximum, it is higher than all of the points that are immediately nearby. So, if you take a look at this little graph that I drew, this point, this local maximum, it is higher than all of the points that are in the immediate vicinity. Now, a local minimum, which is what this is down here, a local minimum occurs when it is the smallest y-coordinate among all of the points that are immediately nearby. So, if you take a look at this little graph here at this local minimum, it is the point that is lower than all of the points that are immediately nearby, so that is a local minimum. Now, in some cases, local extrema can be the same as absolute extrema. In some cases. In the cases where the absolute extrema occur at an interior point, that is when a local extrema is the same as an absolute extrema. However, in some cases they are not, because remember, absolute extrema can occur at endpoints. Local extrema always occur at interior points. So local extrema always occur at interior points of the interval in question. Absolute extrema could be at endpoints, but local extrema are not at endpoints. They are only at interior points. Now remember, you can have some overlap. When an absolute extrema occurs at an interior point, that means a local extrema and an absolute extrema will share the same point, but a lot of times they are not. So this graph here kind of sums up a little bit of all of this. This endpoint here at A, this is the absolute minimum, because there is no smaller value than this point here at A. So this is the case where the absolute minimum occurred at an endpoint. Now this right here is what is called a local maximum, because of all of the points that are in the immediate vicinity, this point is the highest among all of the points in the immediate vicinity. This point right here is what is called a local minimum, because it is the lowest point of all of the points that are in the immediate vicinity. Now these, this local maximum over here and this local minimum over here are not the highest and lowest points on the entire graph, but they are higher and lower than the points that are immediately nearby. Now this point way up here, this is an interior point. It is a local maximum because it is higher than all of the points that are immediately nearby. So it does fit the criteria for a local maximum. However, it also happens to be the highest point on the entire graph, so it is also an absolute maximum. So this point right here at E is both an absolute maximum and a local maximum. Now this point over here at B, this is just an endpoint. It's really nothing special. It's not an absolute extrema and it can't be a local extrema, so that's really all it is. It's an endpoint, nothing special. This is the technical definition of local maximums and minimums. Remember, I'm never going to ask you to recite a definition or define something on your own words on an exam. But basically, if if the y-coordinate at a specific point is greater than everything else in the immediate vicinity, you have what is called a local maximum. And if a y-coordinate is smaller than all the ones in the immediate vicinity, you have a local minimum. So what we're going to do for this next one is we are going to take this function, y equals f of x. We're going to identify the absolute extrema, and we are going to identify the local extrema. Let's start with the local extrema. Those are the peaks and valleys, the points that are higher or lower than the ones that are immediately nearby. We'll start with the local maximums. There is a local maximum here at Q, and there is a local maximum here at S. So a local max at Q and a local max at S. Now for the local minimums, there is a local minimum here at P. And there is another local minimum here at R. Because those are the points that are lower than the ones that are immediately nearby. Now, for the absolute extrema, those are the highest and lowest points respectively. So, looking at this local min right here, this is also the lowest point on the entire graph. So this also happens to be the absolute minimum. The absolute max is actually going to occur both at Q and at S. Because remember, you can have 2 points if they have the same y-coordinate, and that y-coordinate is the biggest one on the entire interval, it counts as an absolute extrema. So both of these, both Q and S, are also absolute maxes. And they are tied for absolute max. A and B there, endpoints, nothing special. Now, I do promise that all of this does have to do with derivatives, so what we're going to do is we're not only going to identify the local extrema on this little graph here, we're also going to identify what the slopes of the tangent lines are on either side of those local extrema, decide whether the derivatives are going to be positive or negative. So let's start with just identifying the local extrema. We got a local max here at B. We got a local maximum here at D, and we've got a local minimum here at C. Now, for the derivatives, the slopes of the tangent lines, remember that is directly tied to whether the function is increasing or decreasing. So if you start at the endpoint A and you trace the graph from left to right, on the interval from A to B, the function is increasing, so that means that all of the derivatives are positive because the slopes of the tangent lines are all positive. So the derivative is positive. Now, between this maximum at B and this minimum at C, the function is decreasing. That means all of the tangent lines are negative, so that means the derivatives are negative. Then, between C and D, the function is increasing again, which means the slopes of the tangent lines are all positive, so that means that the derivative is also positive. And then between this maximum and this endpoint here at E, the function is decreasing again. The tangent lines all have a negative slope, so that means that the derivative is also negative. So what does that mean, in terms of the maximums and minimums? Well, at this local max right here, on either side of that local maximum, the derivative switched from positive to negative. And then it did here again at this local max. The derivative switched from positive to negative on either side of that local maximum. So at your local maximums, the derivative, the first derivative, switches from positive to negative. Now, at this local min down here at C, the derivative switched from negative to positive. So on either side of a local minimum, the derivative switches from negative to positive. Now, local maximums and minimums always occur at what are called critical points. You definitely need to write this down, and no, I won't ask you to recite the definition of a critical point. You do need to know the definition of a critical point because you are going to be using it a lot. So a critical point is always an interior point. That's actually really important, that critical points are always interior points. So an interior point C in the domain where the first derivative is equal to 0, or the first derivative fails to exist is what is called a critical point. So critical points are interior points where the derivative is either equal to 0 or where the derivative fails to exist or is undefined. Those are what are called critical points. So that's the only criteria in order to be a critical point. The first derivative either equals 0 or the first derivative is undefined. So what that means about local extrema, if you have a local minimum or maximum and the derivative exists, that means the derivative is equal to 0. So what that means is that local extrema always occur at critical points. Always. However, the criteria to be a critical point is that the derivative just equals 0 or that the derivative just fails to exist. So not every critical point is a local extrema. So not every critical point is a local extrema. I am really sorry for how bad my handwriting is on this. So this graph just kind of, summarizes a little bit of all of that. So, we have an absolute minimum occurs right here at A, and the absolute maximum occurs right here at C4, that interior point. Now, the absolute minimum occurred at an endpoint, the absolute maximum occurred at an endpoint. This absolute maximum is also a local maximum, because it does fit the criteria for a local maximum. It is higher than all of the points that are immediately nearby. However, if you take a look at this point, this is a sharp point. We learned about these way back in early chapter 3 when you guys first learned derivatives. Those sharp corner points are not differentiable, so that means the derivative is undefined there. So it is still a critical point. It does fit the criteria for a local maximum. And it is an absolute maximum because it's the highest point on the graph, but the derivative is undefined there. Now, we also have a local maximum over here at C2, and this is a point where the derivative equals 0. So then we also have a local minimum down here at C3, and this is where the first derivative is equal to 0. However, like I said on the previous slide, not every critical point is a local extrema. Local extremas are higher or lower than all the points that are nearby. The only criteria to be a critical point is that the derivative equals 0 or the derivative is undefined. So if you take a look at this point right here at C1, the first derivative is technically equal to 0. So it's technically a critical point. However, it is not a local min or max. It's neither. It's one of those saddle points. So yes, saddle points will have a derivative equals 0, so critical points, can also include those saddle points as well. Then we have the same situation going on here at C5. Yes, the derivative is equal to 0, but this is not a local min or max, so it is not a local extrema. So be very careful of critical points. So this first one over here, this is an example, this is technically a local minimum, technically. This is an example of a local minimum where the first derivative does not exist because it's got a point of discontinuity. And if you remember from early chapter 3, if a function is not continuous, it's automatically not differentiable. So the derivative does not exist and it technically has a local minimum. And this is an example of a local maximum where the first derivative does not exist because, again, those corner points, not differentiable. However, not every critical point is a local extrema. So this is an instance where the first derivative equals 0, but there is no local maximum or minimum. It's one of those saddle points. This is an example where the derivative does not exist, because remember, vertical tangents, the slope of a vertical line is undefined, so technically the derivative is undefined, but there is no local minimum or maximum. So, just to kind of summarize, this slide is kind of important. Local extrema always occur at critical points. Local extrema always occur where the derivative is equal to 0, or where the first derivative is undefined. This does not mean that every single critical point is a local extrema. We've seen a bunch of examples. Now, absolute extrema can occur at one of two places. They can occur at a critical point on the interior, or they can occur at the end point on a closed interval. So definitely make sure that you copy down this slide, because this slide kind of summarizes everything and is extremely important. We're going to focus first on the absolute extrema. They occur at at one of two places, either at critical points on the interior or at endpoints. So we are actually going to be locating absolute minimum and maximum values without a graph, because this is actually very easy to do without even looking at a graph if you remember that absolute extrema only occur at critical points or at endpoints. So here's how to locate absolute minimums and maximums without a graph. First thing you're going to do is you're going to find the critical points. So you're going to find the first derivative, set it equal to 0, and then, if applicable, also figure out where the first derivative does not exist. Now these points are candidates for the absolute minimums and maximums. To actually find the minimums and maximums, what you're going to do is you're basically going to make an XY table. You're going to plug in all of the critical points, and you're going to plug in all of the endpoints. So you're going to evaluate the function at both the critical points and the endpoints. No, you don't use the derivative. You're actually done with the derivative. Absolute extrema deal with the actual y-coordinates, so we're going to be dealing with the original function. So you're going to evaluate the original function at both the critical points and the endpoints. Whichever point has the smallest y-coordinate is the absolute minimum. Whatever point has the largest y-coordinate is the absolute maximum. So we're going to do that for this first one. We're going to take this function f of x equals x to the fourth minus 2x cubed on the closed interval -2 to 2, and we're going to find both the absolute maximum and the absolute minimum. So first of all, the function is a polynomial, therefore it's continuous, and we have a closed interval. So the extreme value theorem does apply, which means that we are guaranteed to have both an absolute maximum and an absolute minimum on this interval. So starting with the the first thing we got to do is we have to find the critical points. To find the critical points, what we're going to do is we're going to evaluate the first derivative. So we're going to find the first derivative, which is going to be 4x cubed minus 6x squared. Then we're going to set the first derivative equal to 0. And we're going to solve for x. Now, because it's a polynomial, we don't have to worry about where the derivative is undefined. We just have to worry about where the first derivative would equal 0. So, if you notice, there's a common factor of 2x squared, so I'm going to factor out a 2x squared out of both of these terms. Gives us a 2x minus 3. So we're going to have two critical points here. We're going to have one critical point occur when, at x equals 0. And the other critical point is going to occur where 2x minus 3 is equal to 0, which gives us an x-coordinate of 3/2 or 1.5. And remember, these are candidates for the absolute extrema. To actually find what the absolute extrema are, what we're going to do is we're going to basically make an xy table. We're going to make an f of x table, and we're actually going to evaluate the original function at both the critical points and at both of the endpoints. And so we have -2, and then we have 0, and then 3/2, and we have 2. Whatever point has the biggest y-coordinate is the whatever point has the biggest y-coordinate is the absolute maximum. Whichever point has the smallest y-coordinate is the absolute minimum. And yes, at this point, you can either evaluate this by plugging them all in, or you can generate a function on a graphing calculator, whichever. And then you're going to evaluate each of these. Now, give me one moment. I do have to pause the recording really quick. Technical troubles on this end, so I am actually going to have to pause the recording real quick, and I will be right back. Okay, and we're back. Sorry about that. No, what are you doing? Go away. All right, there we go. I'm also hoping that the audio was both, recording and able to be heard. So we'll see. This section is unfortunately the first full-length lecture video I'm attempting. So unfortunately, this section's the guinea pig. So I got to change the pointer again. Oh my goodness. This will get easier as I get used to it. All right, anyway, so if you evaluate the original function here at -2, you do get a y-coordinate of 32. If you evaluate the original function at 0, you get 0. If you evaluate the original function at 3/2, you get -27 over 16. You can also give a decimal to it, doesn't really matter. And if you evaluate the function at 2, you get 0. Now, whichever point has the biggest y-coordinate is the absolute maximum. So this point right there, this -2, 32, this is the absolute maximum. The absolute maximum occurs at it is 32, and it occurs at x equals -2. Now, the absolute minimum is the smallest y-coordinate. So since this point has the smallest y-coordinate, this is the absolute minimum. So the absolute minimum is -27 over 16, and it occurs at 3/2. Now, 0, 0, and 2, 0 are neither local maxes nor local mins. We don't really know what they are at this point, just with this information, but we don't know that they are absolute maxes or absolute mins. Now, for this next one, we're going to take this function and we're going to find its absolute extrema on the closed interval -1 to 2. So because finding absolute extrema is going to involve critical points, which is going to involve derivatives, I really don't want to use product rule right now. So what I'm going to do is I'm actually going to distribute this x to the power of 2/3 so that I don't have to use product rule. So what that gives us is 2x to the power of 2/3 minus, add the powers, we get x to the power of 5/3. So first step to finding absolute extrema is we're going to find the critical points. To find the critical points, we're going to find where the first derivative is either equal to 0 or where the first derivative is undefined. So let's actually find the first derivative. So g prime of x, use power rule, move down the power of 2/3. 2 times 2/3 is 4/3. And decrease the power by 1, 2 over 3, minus 3 over 3 is -1 over 3. And then minus, move down the power 5/3. Decrease the power by 1, 5/3, minus 3 over 3 is 2/3. And yes, we're going to have to set this thing equal to 0, and then we're also going to have to find where it is undefined. Now, as the second that you see a negative exponent, you do need to be thinking variables in the denominator. Variables in the denominator do mean that it is possible for this derivative to be undefined somewhere. Now, right now, it's not really workable as is. So here's the thing about fractions. A fraction is equal to 0 when the numerator equals 0. A fraction is undefined when the denominator equals 0. So if we can somehow combine these two terms into one singular fraction, all we have to do to figure out where the first derivative is equal to 0 is set the numerator equal to 0, and then to find where the fraction is undefined, we set the denominator equal to 0. So that's what I'm going to start doing. Now, if you notice, both of these fractions do technically have a common denominator of 3, so I'm going to kind of combine these with that common denominator 3. So I'm going to write this as 4x to the power of -1/3 minus 5x to the power of 2/3 all over 3. Then, in the numerator, both of these terms have an x in it, and the rule when your greatest common factor is a variable is the exponent on that greatest common factor is the lowest power of x that appears. Since the lowest power of x that appears is -1/3, I'm going to factor out an x to the power of -1/3 out of both of these terms. Now, you might remember that when you factor out a variable, what you're going to be doing is you're going to be taking each of the existing exponents and you're going to be subtracting the power on your greatest common factor. So we're going to be taking each of these exponents and we're going to be subtracting -1/3. So I'm going to leave the 4 alone. -1/3 minus -1/3 is 0. So x to the power 0 cancels out. Then you're going to leave the 5 alone. So 2 over 3 minus negative 1 over 3 is x to the power 1. Now that this is written as multiplication, now you can take that x to the power of negative 1/3 and move it into the denominator to become x to the power of positive 1/3. So the denominator is now 3x to the power of positive 1/3. And the numerator is 4 minus 5x. So this is the first derivative just written as a singular fraction. So the first derivative is equal to 0 when the numerator, 4 minus 5x, is equal to 0. And if you solve this for x, you get a critical point of x equals 4/5. So there's one critical point. However, as soon as you see variables in the denominator, you do start have to thinking about where the first derivative is undefined. So the first derivative is undefined when the denominator, 3x to the power of 1/3, equals 0. And if you solve this for x, you get x equals 0. So these are your critical points. They are candidates for the absolute extrema. So remember, in order to actually find the absolute extrema, what you're going to do is you're going to make an g of x table. And you're going to evaluate the original function g of x at each of these critical points and each of the endpoints. So we're going to be plugging in -1, we're going to be plugging in 0, we're going to be plugging in 4/5, and we're going to be plugging in 2. Whichever point has the biggest y-coordinate is the absolute maximum. Whichever point has the smallest y-coordinate is the absolute minimum. Keeping in mind that we're dealing with the original function, we're actually done with the derivative. So if you evaluate the original function at -1, you get a y-coordinate of 3. If you evaluate the original function at 0, you get 0. If you plug in 4/5, it's a decimal, so you get about 1.03-ish. And if you plug 2 into the original function, you get 0. All right, so let's start with the absolute maximum. The absolute maximum is actually right there. It has the biggest y-coordinate, so that is the absolute maximum. And there are actually 2 points that are tied for absolute minimum. The smallest y-coordinate appears to be 0, and it occurs twice, once at 0, 0, and once at 2, 0. So those two tied are the absolute minimums. Absolute minimum is 0, and it occurs at both 2 and at 0. Now, just for the sake of time, this video is getting a little long. We are going to move on to Rolle's theorem, unfortunately. I am keeping in mind the file size. So, for this next section, Actually, you know what? I'm going to stop the recording here, and I'm going to make mean value theorem its own video. So, just for the sake of file size, I am going to make the mean value theorem, which is section 4.2, its own separate video. So, thank you all for watching, and I hope that this was helpful. And if you guys do have any questions, please don't hesitate to send me an email or a message in Canvas. Goes to the same place, and I can respond to your questions in either place. So thank you all very much, and I will see you in the next section for mean value theorem. Bye-bye.